Welcome to Brain Vision.
Hi everyone, so what we have is a hot air balloon that is releasing hot air to undergo performing some maneuvers. So we're going to head and write down the given information for this air release flap on this hot air balloon. So we know that the pressure is 100 kPa, the temperature is equal to 35 degrees C, which is equivalent to 308 Kelvin. The velocity V1 is 2 meters per second, and that velocity V1 is the velocity of hot air entering the balloon. And velocity V2 is equal to 1 meter per second, and that's the velocity of the air leaving through this air release flap. We have an area 1, which is equal to 1 meter squared, and that's the filling opening, and area 2, which is equal to 0.5 meters squared, and that is the air release opening area. This maneuver is lasting 2 minutes, so we're going to go ahead and write that in seconds as 120 seconds, and the initial volume of this balloon is 75 meters cubed. What we're asked to find is the final volume of the balloon, so that's going to be VF, and the work produced by the air inside the balloon as it expands the balloon skin. So what we're going to do first is go to our table and find our air gas constant. So we'll find that R is equal to 0.287 kilojoules per kilogram Kelvin. And by using the ideal gas law, which is P equals rho RT, we can actually solve for the density of this air by solving for rho. So therefore rho is going to equal P over RT. And plugging in for these quantities, we'll find that the density of our air is equal to 1.1313 kilograms per meter cubed. Next, what we're going to do is actually solve for our change in volume. So delta V, the change in volume, is going to equal the change in m dot over rho. Now m dot is the mass flow rate, and that's defined as rho times area times velocity. So if we're going to apply this concept to find the delta V. So we can say that delta V is equal to m dot 2 minus m dot 1 all over rho times delta T. Yes, there should be times delta T here. And if we expand upon this and apply this definition, we'll see that this delta V is just equal to rho times A2 V2 minus A1 V1 all over rho times delta T. As you can see, these rho's cancel out. Therefore, our delta V is just equal to A2 V2 minus A1 V1 all multiplied by delta T. And these are all quantities that are actually known to us, so we can go ahead and say that delta V is equal to negative 180 meters cubed. So remember that we defined delta V as being equal to V1 minus V2. So if we're going to solve for a final volume, that's V2, we can say that V2 is going to equal V1 minus delta V. Recall that V1 is equal to 75 cubic meters, so plugging that in for V1 and negative 180 cubic meters for delta V, we'll find that V2 is equal to 255 meters cubed. So our balloon has actually gotten bigger. Next, what we're going to do is go ahead and just solve for the work produced by the air inside the balloon as it expands that balloon skin. So work is equal to negative P times delta V. And plugging in for these quantities, recall that P is 100 kPa and that our delta V is negative 180 cubic meters. And what this gives us is a total work done of 18 megajoules. And that is our final answer.